In this example, we have a 5.00 kilogram flower pot suspended by two strings. And the question is, what's the tension on each string? Well, we know the flower pot isn't moving, so the sum of the forces on the flower pot must be 0. What are the forces at play here? Well, each string has a tension that's pulling up on the flower pot. We'll call the first string's tension T1 and the second string's tension T2. Gravity is pulling down on the flower pot, and we'll label that force W. Now we clearly have a two-dimensional problem here. Gravity's pulling straight down, but those tensions are both pulling off at an angle. So we're going to have to treat this with two-dimensional vectors. So we might as well first go ahead and break each vector up into its x and y components. Well, let's start with T1. The x component of T1 is given by the magnitude, T1, times the cosine of the angle, 30.0 degrees. That gives us 0.866 T1. The y component of T1 is the magnitude once again, times the sine of the angle. That gives us 0.500 T1. T2 is a little more tricky because the angle given for T2 is not defined properly. We have to define our angles from the positive x-axis. So the angle we really need for T2 is the red angle drawn there. What is that angle? Well, from the positive x-axis to the negative x-axis is 180 degrees. 40 degrees of that is already used up by the angle shown. So that red angle must be 140 degrees in order to make the total angle 180. So the properly defined angle for T2 is 140.0 degrees. Let's use that angle in calculating the x and y components. So the x component of T2 is T2 times the cosine of 140.0, or negative 0.7660 T2. The y component is T2 times the sine of the angle, which is 0.6428 T2. Okay, we have one more force to consider here, the weight that's pulling down on the flower pot. Now, I didn't give the weight in the problem. I gave you the mass, 5.00 kilograms. I'm going to assume by now that you know how to convert from mass to weight. So the weight that corresponds to 5.00 kilograms is 49 newtons. So that's the magnitude of the weight. What are its x and y components? Well, the weight's pulling straight down, so its angle is 270.0 degrees. So the x component of the weight is the magnitude, 49 newtons, times the cosine of 270.0 degrees. That turns out to be 0. The y component is the magnitude, 49 newtons, times the sine of 270.0 degrees, and that turns out to be negative 49 newtons. Okay, now we have the x and y components for all of our force vectors. Now let's look at each dimension and sum up the components so that they all equal 0. In the x dimension, T1x is 0.866 T1. T2x is negative 0.7660 T2. And the weight's 0. So 0.866 T1 plus negative 0.7660 T2 have to sum to 0. Alright, well this equation has two unknowns in it, but we'll go ahead and solve for one of the unknowns in terms of the other. Let's solve for T2 in terms of T1. Well, I've got to add 0.7660 T2 to each side of the equation. That gives me 0.866 T1 equals 0.7660 T2. Now I can divide both sides by 0.7660, and I find out that T2 is really 1.13 times T1. Okay, now that's a relationship between these two tensions, so let's remember that. T2 equals 1.13 times T1. Alright, well that doesn't give us our answer, but we have one more dimension to look in yet. We have to look at the y dimension and make sure the forces sum up to 0 in the y dimension as well. T1y is 0.500 T1. T2y is 0.6428 T2. And wy is negative 49 newtons. Those all have to add up to 0. Now this equation also has two unknowns, but remember, we have a relationship between those two unknowns. We know that T2 equals 1.13 T1. So in this equation, let's substitute 1.13 T1 in for T2. When we do that, we find that 0.500 T1 plus 0.6428 times the quantity 1.13 T1 minus 49 newtons equals 0. Now look what we have. We have an equation with just one unknown. We can group the T1 terms together and find that 1.226 T1 equals 49 newtons. Well, that gives us an answer for T1. When we divide both sides by 1.226, we find that T1 is 4.0 times 10 to the 1 newtons. Now notice, this has to be reported in scientific notation. I need two significant figures because of the 49. If I wrote the answer as 40 newtons, that'd only be one significant figure. So this answer requires scientific notation, 4.0 times 10 to the 1 newtons. All right, that's T1. The problem asks for both tensions. How do I get the other tension? Well, I already know that T2 equals 1.13 times T1. So if I take my value for T1 and multiply by 1.13, I get T2. So T2 is 45 newtons. Now we have both tensions. And therefore we have our answer.